Okay, so at this point we have covered the basic idea of measuring angles, radians versus degrees. We've looked at some of the history of how trigonometry was studied. And now we're going to start looking at the actual unit circle. And we're going to build it up. But first, let's remember what we know. Let's write down the 6 shortcuts for the trig functions. So you may remember so, ka, toa. You might even remember how to use it. What this so, S-O-H, is saying is sine equals opposite over hypotenuse. I'm going to write it again. I'm going to say sine equals opposite over hypotenuse. And yes, I should have a theta there, but I'm being lazy and not writing it because it's late at night and I have a lot of videos to make. So sine equals opposite over hypotenuse. Ka, C-A-H, is saying cosine equals adjacent over hypotenuse. Toa is saying tangent equals opposite over adjacent. And maybe you recall a way that one of your former teachers, not me of course, taught you to remember so ka toa. But I think that's pretty ingrained in us at this point. So ka toa, even if you don't know what that means or what trigonometry is, you've probably heard so ka toa. That's what it's saying. But you may notice this says, what are these 6 trig functions? Well, this is only 3. So we need to remember the other 3 trig functions, which are the reciprocal identities. So the reciprocal of sine is the cosecant function, abbreviated CSC. Cosecant is a reciprocal, so flip the fraction, h over o. The reciprocal of cosine is secant, and that again, we'll flip that fraction to give us h over a. The dorky joke that Mr. Lair always says is when he sends me something funny in a text message, instead of saying LOL, he says seek, 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 because it is ha 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 ha. So yes, we are dorky. The reciprocal of tangent is cotangent, and again, flip it, so a over o. So we have SOHCAHTOA to remember sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. And we have CHO, SHA, COW to confuse us and not remember that the reciprocals identities are cosecant is hypotenuse over opposite, secant is hypotenuse over adjacent, and cotangent is adjacent over opposite. But being realistic, the way I remember it is cotangent obviously goes with tangent, and then the question is, does cosecant go with sine, or does cosecant go with cosine? Does secant go with sine, or does secant go with cosine? Well, I remember that it's backwards. Sometimes the best way for me to remember something when it's weird is to just remember that it is weird and is not what I would think it is. So the sine goes to cosecant because the s changes to a c, and the cosine goes to a secant because the c changes to an s. So however you can remember it, you absolutely need to know these 6 identities right here. So now let's jump into building the unit circle and think about where these points come from. So 2 quick geometry questions. What does it mean for a triangle to be isosceles? Well, that means that it has 2 legs that are congruent, aka the same length. And the consequence of that is the 2 base angles will also be congruent. The top angle right there is called the vertex angles. These are the legs. This is the base, and these are the base angles. Okay, that is an isosceles triangle. What does it mean for 2 triangles to be similar? Well, 2 triangles are similar if they have the same angles. The legs will not be the same as the size of the legs of the original triangle, but they will be an enlarged version of that. I like to think of it as you took a triangle and you enlarged it. You multiplied each leg by some value to increase the size. So if this was, say, 3, 3, and 5, maybe this is 9, 9, and 15. Maybe everything's multiplied by 3. But the angles are all the same. Those are similar triangles. You can multiply them by a scale factor to get the other one. So let's do this. Let's draw an isosceles right triangle with legs of length 1, and let's calculate the length of the hypotenuse. So I draw a triangle right there. These legs are congruent. They have a length of 1. Well, I failed to mention this. It's an isosceles right triangle, and I'm going to redraw this because it's totally not to scale. What we want to draw is a right triangle whose vertex angle is a right angle with legs of length 1, because now that it's a right angle, we can use Pythagorean theorem, which says the legs squared and added together will equal the hypotenuse squared. So we get 1 squared plus 1 squared equals the hypotenuse squared. So 1 squared is 1, 1 squared is also 1, 1 plus 1 is 2, so the hypotenuse squared is 2, so the hypotenuse is the square root of 2, which you may remember from that Weihart video, is an irrational number, which very much angered the Greeks. But we get this nifty little triangle right here. But let's take that triangle and let's multiply it by a scale factor to get a hypotenuse of length 1. So I'm going to copy this and steal it and bring it over. If I take that triangle and I multiply each side by some value, I want to get this hypotenuse, the square root of 2, to equal 1. Well, what's the easiest way to get a value to equal 1? Divide it by itself. So let's divide everything by the square root of 2. So that divided by the square root of 2, that divided by the square root of 2, and that divided by the square root of 2. And let's simplify this. So I'm going to get this triangle right here. All my angles and sides are the same. What are these angles? Well, they're 45 degrees because they have to be congruent, and we have a right angle up top. Sorry, that's an ugly 45. But I get in the bottom that hypotenuse is now length 1. And what about the legs? Well, 1 over square root of 2, we need to rationalize that. So we need to multiply it by the square root of 2 over 2, which will give us, oh, I lied, I just did a Freudian slip. Multiply it by root 2 over root 2. In the denominator, root 2 times root 2 is 2. In the numerator, 1 times root 2 is root 2. So we get root 2 over 2, and the same for the other leg as well. So now all I've done is rotate that triangle so it looks a little more like we're used to seeing a right triangle with that right angle down there. And now we want to calculate the values of sine, cosine, and tangent for this 45-degree angle. Well, it becomes very easy at this point because we know that sine of the angle is the opposite side, which is that side right there, which is the square root of 2 over 2, divided by the hypotenuse. But the hypotenuse is 1, so we get sine of 45 is root 2 over 2. And we can do cosine of 45 is the adjacent, which is that side, over the hypotenuse, which is again is 1. So I again get root 2 over 2. And then we can do tangent of 45, which is the opposite over the adjacent, but they're both square root of 2 over 2. So I get 1. But we need to think of this in terms of radians. So sine of 45 is the same as sine of pi over 4 radians. Cosine of 45 is the same as cosine of pi over 4. And tangent of 45, is the same as tangent of pi over 4. If you can't remember that, what I do is I draw myself a little reference unit circle. I know that 90 degrees, well, what do I know? I know that 180 degrees is the same as pi, so 90 degrees is pi over 2, and so 45 degrees is pi over 4. I'm just dividing by 2 each time, and that makes it very simple to remember. But these numbers right here, you will absolutely need to know on the tip of your tongue without a calculator or any hesitation whatsoever. You need those values. And now let's look at the next special triangle. So for our next angles, we're going to need to think about what an equilateral triangle is. Well, an equilateral triangle is a triangle where all sides are the same length. And again, a special consequence is that all of the angles will be the same length as well. That's cool. So if they're all the same and there's 180 degrees total, 180 degrees divided by 3 is 60 degrees for each of those angles. Then the next question is, what is an altitude of a triangle? Well, an altitude of a triangle is a line that goes from a vertex perpendicular to the opposite side. You could even have some awkward scalene triangle like this, and the altitude would go straight down like that, even though that side doesn't extend out. But that's just a little geometry to think about. How does that apply to trig? Well, let's draw a equilateral triangle with side lengths of 2. Let's drop that altitude down. A special consequence of dropping an altitude in an equilateral triangle like this is that it will split the side in half. So if we focus on just the left half of this triangle, we have a right angle there because it was dropped down. This side is still 2. This side was split in half, so it's 1. We can use Pythagorean theorem to figure out that this side right here is going to be the square root of 3. A squared plus b squared equals c squared, so 2 squared minus 1 squared equals the other side. 4 minus 1 equals 3. That's squared though, so take the square root. And another special consequence is that the angle that the altitude drops from gets bisected. So this top angle up there is 30, and this bottom angle down there is 60. So we get this special triangle, and we're going to do something similar to what we just did for that 45, 45, 90 triangle. We are going to multiply it by a scale factor to get a hypotenuse of length 1. Again, the idea is we could then plop this on a unit circle. So the hypotenuse is currently 2, so we need to divide everything by 2. So we get our triangle with a hypotenuse of 1. 1 divided by 2 is 1/2, and root 3 divided by 2 is just root 3 over 2. And again, right angle, 60 degrees, and 30. So now we're going to have two tasks, just like we did before. We're going to want to list the sine, cosine, and tangent values for that 30-degree angle. So let's, where am I? Oh no, that was not what I wanted. Hold on. Okay, so sine of 30 degrees is opposite of the sine angle is 1/2 divided by the hypotenuse. Again, hypotenuse is just 1, so we just get sine of 30 is 1/2. Okay, cosine of 30 then is going to be root 3 over 2, because cosine is adjacent. Root 3 over 2 is the adjacent side, and the hypotenuse is 1. So again, doesn't do anything. Tangent is a little more involved. Tangent of 30 degrees. Tangent is opposite, which is 1/2, over adjacent, which is root 3 over 2. Those 2's cancel. We get 1 over root 3. Rationalize that by multiplying by root 3 over root 3. We get root 3 over positive 3 for the tangent of theta. But again, in radians, sine of 30 is the same as sine of pi over 6. And then again, cosine of 30 is cosine of pi over 6. And tangent of 30 is the same as tangent of pi over 6. Just like before, draw yourself a little pinwheel. We know we have a 90-degree angle straight up, and 90 divided by 3 is 30. 90 is the same as pi over 2, so divide that by 3 to get pi over 6, just like that. And now let's list the values of the trig functions for that 60-degree angle. So sine of 60 is going to equal the opposite, which is root 3 over 2, over the hypotenuse, which is 1, so it doesn't do anything. Cosine of 60 is going to equal the adjacent, which is 1/2, over the hypotenuse, which is 1, so it doesn't do anything. And tangent is going to equal the opposite, which is root 3 over 2, over the adjacent, which is 1/2. The 2's cancel, and we're left with root 3. And again, what is the equivalent radian? Well, if 30 was pi over 6, then 60 has to be 2 pi over 6, which is pi over 3. So sine of pi over 3, cosine of pi over 3, and tangent of pi over 3. And again, these are values that you need to be very familiar with. So if you're not currently very familiar with these values, you need to practice with them a bunch until it becomes second nature, because you can't do anything in this unit if you don't know these values. So now we're going to talk about a big part of what we do with the unit circle. We know that on the unit circle, the radius is 1. That's why it's called a unit circle. And we want to explain why the x value of a point on the circle corresponds to cosine. So why is x equal to cosine of theta? And why is y equal to sine of theta? Specifically on the unit circle. So let's draw some random angle there with the point x comma y. The radius is 1, so that's 1. And we can draw our little right triangle with our theta value right there. Well, this opposite side of that theta is y value, and the adjacent side is the x value based off of the point of that top point there, x comma y, since it's a right triangle. So we'll think about what is sine of theta. Sine of theta is opposite of our hypotenuse. Opposite is y, hypotenuse is 1. Cosine of theta is adjacent over hypotenuse. Adjacent is x, hypotenuse is 1. The 1's don't do anything, so we get those lovely values right there. So cosine corresponds to x, and y corresponds to sine. So now let's go ahead and plop all these values in. We need to absolutely know how to use this unit circle. So first off, first quadrant, 0 degrees is equivalent to 0 radians. X value right there is going to be the radius, which is 1, and the y value is 0. We haven't gone anywhere. We can fill the top one out as well. 90 degrees is pi over 2 radians. Losing my voice from talking again. Golly. 90 is pi over 2, and 90 degrees is straight up and down, hasn't moved left or right, so x is 0 and y is 1. Okay, right here, 180 degrees is the same as pi radians, and same idea here, except we're out to the left, so x is negative 1, and y is still 0, because we're on the x-axis. Straight down, we have 270 degrees and 3 pi over 2 radians. X value is still 0, y value is negative 1, because now I'm going down. So those values should be pretty straightforward to get. And now we need to figure out the other ones. Well, let's fill out the first quadrant, and then let's use symmetry. So this first line here, 30 degrees, is the same as pi over 6 radians. And these are the values that we figured out from those triangles. The x value is root 3 over 2. The y value is 1/2. And if you can remember those two special values but can't remember which is which, this is what I do. If you think about a little triangle you could draw, a little fake unit circle, look at where this point lies. The x value there is very clearly much more than half of that distance. Whereas if you compare this y value to that total unit circle distance, that distance and that distance is much more reasonably 1/2 of that total distance. So I remember that, and I remember that sine is my y value, and I get those points right there. Okay, well, what's special about the next point, which is 45 degrees? Well, 45 is the same as pi over 4, and I remember that these 2 points are the same, and they really only include one number to remember. We get root 2 over 2 and root 2 over 2. They are the same. That is nice. Well, the next line is going to be our 60-degree angle, double the 30-degree angle. So we get 2 pi over 6, which is the same as pi over 3. And this point is special because it flips the x and the y values of the 30-degree angle. So I get x is 1/2 and y is root 3 over 2. So once you get those values, you should be able to use symmetry to figure everything else out. The radian values are really easy to figure out because I get pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, which is the same as 2 pi over 3, 5 pi over 6, right there, and then 6 pi over 6, which is pi, and then 7 pi over 6, and 8 pi over 6, which is the same. 8 pi over 6, reduce that by 2, you get 4 pi over 3. And keep going through 4 pi over 3, and then we get 5 pi over 3. Sorry, I goofed up. We got the 4 pi over 3 there, which came from 8 pi over 6. So the bottom is 9 pi over 6, reduces to 3 pi over 6. And then here we get 10 pi over 6, which is why that reduces to 5 pi over 3. And here we get 11 pi over 6. And then finally, one full revolution gets us 12 pi over 6, which is the same as 2 pi. So I'm just counting by sixths there all the way around. And at this point, all I need to do is use symmetry. Think about this line versus that line. How does the x values compare and how do the y values compare? Well, they're both these same little reference triangles right there. So those x values are the same but opposites because we are to the left of the origin. The y values are exactly the same. So, right here, I get negative 1/2, and I still get positive root 3 over 2. X values here on this 45-degree angle in this quadrant is the same as, if you think of 1 pi over 4, 2 pi over 4. This is 3 pi over 4, so counting by fourths now. The only difference is the x value is negative, so I get negative root 2 over 2. Y value is still positive, root 2 over 2. Okay, next one, 5 pi over 6. Oh man, this is bad. I wrote 45 degrees there. It shouldn't be 45 degrees. 90 plus 45 degrees, I think, is 135 degrees. So we get that right there. And let's fill this other stuff in too. 90 plus 30 gives me 120 degrees right there. And then add another 30 to that. We get 150 degrees for that angle right there. 5 pi over 6. Well, it's going to relate back to those values right there, except the x value is going to be the opposite. So we're going to get negative root 3 over 2. And again, still positive 1/2. Notice how all these values are similar to all those corresponding values in the first quadrant. They're the same, except all of the x values are negative. Think about all students take calculus. What this is saying is in the first quadrant, x and y are positive, aka sine, cosine, tangent, and all the reciprocals are positive. In the second quadrant, this is the first quadrant, this is the second quadrant. In the second quadrant, only sine is positive. Sine is the y values. We have sine of theta equals y, and cosine of theta equals x. Sine is positive, which means everything else, other than its reciprocal, which is cosecant, everything else is negative. So cosine is negative. Cosine is our x values. That's why the x values are negative. Then you can go through and use symmetry in the same way. In the tangent quadrant, both x and y are going to be negative. And in the cosine quadrant there, quadrant 4, cosine will be positive, sine will be negative. And you should end up with this. So take a moment and check those values. You should end up with the same. But again, really, you need to focus on this first quadrant because everything else is just symmetry. So have that first quadrant down solidly and then just figure out which quadrant you're in and what functions are positive or negative in that quadrant.